All right, and then now let's look at the graph of some ToolKit functions. Now, what exactly are these ToolKit functions? Now, they just really means some of the very common functions that you must have seen that in your prerequisite course. Like that. But in case my pace here moving too fast and you have missed some of these functions in your previous course, I will have separate video clips introducing how to construct a graph or how to graph these ToolKit functions from scratch. But in the end, because these functions are meant to be very common, and as I said, they should have been introduced in your prerequisite courses. So some of the modern textbooks in these days use a very the good term that I really like it, the ToolKit function. It really emphasizes the fact that these functions are meant to be used and to be seen pretty much anywhere and everywhere you are doing math. Okay, so let's dive in. And so the plan now for the next many minutes here in this lesson, I am going to introduce the function, and then I'm going to just immediately show the graph. Okay, I'm going to introduce another function, and I'm going to show the graph. And then in case anyone, again, as I said earlier, in case any one of you have not seen any of these ToolKit functions in your prerequisite course, then find my supplementary the video clips where I introduce in elementary steps, like a step-by-step instruction of how we graph those functions using either technologies or building the table of values and all that. Okay, but now allow me to get through these ToolKit functions one by one. And admittedly, among different instructors, there's a little bit of a difference between what's to be included in among these ToolKit functions. So for me, maybe for my lesson here, maybe after I finish with whatever I consider as ToolKit function, for some other professors teaching math out there, there may be other functions out there that other professors might also include as the ToolKit functions. So when you learn about these, the point now is that these functions you're about to learn, they are very common, and the graphs of these are good to know them and good to nail them down so that you can use them anywhere. But be open to learning some other ToolKit values. ToolKit functions that in case I'm not covering it here. Okay, so now the first ToolKit function allow me to introduce. So the function that f of x equals a constant c. Okay, and so f of x equals a constant c. So this is just more like a family of functions. It could be f of x equals 5. That's one function on its own already. It could be f of x equals 6. Okay, see, because that letter itself is another variable. It's just not the input variable. The input variable of this function is x. Okay, but we don't see the x variable here. That means once the value for c is given, then regardless of whatever the input value for x is, the function value will the function's output value will remain equal c. And so in that case, like I said, f of x equals c, that constant function could be f of x equals 5, or in some other case it could be f of x equals 6. Okay, but once it's given, then we stay with that. Okay, so now let me quickly demonstrate the idea a little bit. But let's say if f of x equals 5, for example. Okay, then that means when inputs equals 0, the function output equals 5. That's the whole point of being a constant function. When inputs being 1, the function output again equals 5. When function output is given as -10, the function output is again 5. And that's why it's called a constant function once it's given. Okay, once it's defined. So this function, yes, the name, and I've been saying that name, this is called a constant. Okay, it's a constant function. So after this brief introduction of what that constant function is, let's now quickly have a look. So I demonstrated the idea of a constant function by using f of x equals 5 here being a constant function. And it's a positive constant. And in others, there are other constant functions out there where the constant here is a negative constant. It works too. Okay, so now let's quickly have a look at the graph of this function, constant function. So f of x equals 5. This is the graph for that. And now let me have it right on our screen right here. All right, so now here's our graph space right here. Okay, our graph grid right here, and that constant function appears to be, for the graph, it appears to be, the graph here appears to be a horizontal line right here. Okay, so how is that making sense? How is that consistent with the fact that this function is a constant function? Because see, no matter where we're at for the input 0, input is where we're on the x-axis, and output is where it's represented by the vertical height. So no matter where we are on the x-axis, we maintain, this function maintains for us the same vertical height, the same output being 5. And that's the reason why, now reading on the graph right here, when x equals 0, we're at output 5. When x equals 1 that you saw on the board earlier, output equals 5. When x equals negative 10, the output is also 5, and this is why after considering all infinitely many of those inputs, right, we made up the graph here is made up of by a trace of all points where it's lining up into a flat horizontal line right here. All right, and so now briefly think about if it's if it was f of x equals negative 2, for example, from the beginning. Okay, if the function here, instead of going with f of x equals 5 like I've had here, I could have done f of x equals negative 2. And now allow me to use a red ink right here to emphasize, we made a little change here. So it's still in the end it's still in the end a constant function. But now f of 0, same rule, gives output negative 2. That's why it's called constant function, because output is constantly stays at the same value. And minus 2 for that, minus 2 for this. Okay, and so in that way, let's look at how this other constant function is different with the f of x equals 5. Now, if we're looking at f of x equals negative 2 right here, then okay. All right, so now this is the graph for f of x equals negative 2 right here, and then let me put it in a more close-up view right here. Okay, so this red horizontal line, but see earlier when it was f of x equals 5, then the horizontal line was right up here, right crossing through that y equals 5 on the y-axis. But now f of x is defined as a constant function negative 2. F of x equals negative 2, then that horizontal red line now sinks down to y equals negative 2, the whole line horizontally right here. Okay, and that's what it is. And so as a main characteristic, okay, so anytime we're looking at a constant function, have in your imagination, start having in your imagination that you've seen a horizontal line and you see another horizontal line. So generally speaking, anytime we're looking at a constant function, the graph, now I can just close my eyes and draw it. That's the graph, a horizontal line right here. And this value right here, where it crosses with the y-axis, y equals c. It's a flat horizontal line. Okay, so that's the constant function, one among the ToolKit functions. And so this function here is called, a ToolKit function simply because you will see that a lot of times throughout your time learning in mathematics, right there. Okay, so now the next one in our family of all the ToolKit function that I want to introduce here. Let's look at the next one here, where it's a specific one. F of x equals x. F of x equals x. This is one specific function. F of x equals x. Okay. As far as the name, this function is called the identity, specific name, it's called the identity function. Okay? It's called the identity function. And here's why it's called the identity function. You see, in the way how the function is defined, f of x equals x. This is the rule itself. This is the rule itself. That now I need to mention it. See, it has the rule says for every input, the output will equal exactly the input. The output will equals exactly the input, because the rule said so. Because the rule said so. And so in that way, we can quickly sketch a table of values. I mean, it depends on different problem. I can in some ToolKit function, I built a graph. I just simply handed you with decimals to give the graph. Some other one, I might change approach a little bit. Okay, but now I would like to change the approach here so that I can also blend in my explanation why a function like this is called the identity function. Because for every input, you pick a -2, the outputs, the rule says it's -2. That's why it's called identity, because inputs will give an output exactly equal to where it's currently at. And so now if we go with inputs equals 0, the output is, needless to say, 0. It's a 1000 here. Okay, the output is 1000. So the kind of function where every output, right, is exactly equal to its input right there. That's called the identity function right there. Okay, and so with that quick sketch of the table, and so you can already bring this into your graphing space and plot the points and kind of recognize the graphic there. But now since we have, let me now pop out that graphing device of mine so that you can see what it looks like. All right, so now returning back to our empty graphing space right here, the identity function has this graph right there. All right, so it's a nice slanted line. If we're looking at the graph, and I have had this advice before for anyone looking at learning to read the graph, we're reading a graph from the left to the right. Okay, so now looking at this graph from the left to the right, then the graph is going up. The graph itself, the vertical values are rising. Okay, so from the left to the right, the vertical values on the left here, it was negative, but it's getting less negative vertically. It's getting less negative vertically, then it hits 0, and then it's keep gaining more vertical height right here, being positive. Okay, it's keep getting higher and higher vertically. All right, and then together speaking as a geometric shape right here, this is a line. This is a line, and it's a slanted line, and 45-degree angle made with the x-axis, with the input axis right here. So that's the major characteristic of this identity function, like that. Because, and then here we can also try to get comfortable with reading graph as well. See, for every x value, let's say x equals 2, the estimation, I estimate that the y value is about 2, and it looks just right about there. So that's why we had this point right here. And see, 2, 2. Okay, when input equals 2, okay, we have output equals 2. When input equals 4, okay, or you see for any input, the x value is 3.78, and the output value is also a comma 3.78 as what is read on the board right now, on the graphing space right now. So every input gives an output that's exactly equals to the input itself like that. That's why it's called identity, and due to that nature, we ended up with a slanted 45-degree lines like this, and it made a 45-degree angle with this horizontal input axis. Okay, and that's what the identity function, and that's the main characteristic. And so now from now on, any time that it's rang to your ear that the graph of the identity function, or just anyone talk to your ear about an identity function, then you should have immediately in your mind the picture of here's the x and the y axis, here's the graphing space right here, and it's a nice 45-degree lines right here that going right through the origin. That's good enough to be the function f of x equals x, or in short, in equation notation, y equals x. Okay, and that's why that's the characteristic of this identity function. Okay, and so now before I move on to the next ToolKit function, then the identity function that I introduced here, the graph ended up being a line. on the other hand, back a little bit to the constant function. Okay, back a little bit to the constant function, and here it's just a quick scratch work right here. If it was a constant function, constant c right here, then the graph, I highly advise that it's have this in your imagination. But in the end, the graph here is also a line, and that's the reason why constant function and the identity function and constant function, these two are all being included in a bigger class of functions that's called the linear function, which we will spend some time later on in our time learning together, and you might have seen that already in your prerequisite course as well. I'm quite sure about that. Okay, but so identity function, since the graph itself is a line, nothing more or less, being a line, and then the constant function that I showed previously is also a line. So constant function and identity function are two members in the whole family of so-called the linear function. Okay, linear function. Okay, but there are many other linear functions out there. There are many other functions out there where the graph is a line. So that's also a brief introduction of mine into these terms, like in case you've heard that before, but now at this point when you're learning this, you're not so sure what it was anymore. So that's what it is. So when it says linear function, it means the fact that whatever function that when you draw the graph, when you sketch the graph, or when you generate the graph, it gives you a line. Okay, the graph appears to be a line. Okay, forms into a line. That's called a linear function. Okay. All right, and so now among the ToolKit function, let's now introduce this another function. How about f of x is defined to be the following operation that you've been very familiar with. Yes, there it goes. The absolute value function. Okay, this symbol, the two vertical bars, we call that it's the absolute value. So here it reads absolute value of x. Okay, and so as far as the name, this function is called absolute value. Absolute value function. Okay, it's absolute value function. All right, so let's briefly understand what absolute value does for you. So when you give an input -1, for example, okay, the functions, the rules of the function, see, it's called absolute value because the rule of the function tells us to take the absolute value of whatever input that is. So now when we give this function the input -1, then the rule says take absolute value of -1, which in turn will give a +1. That's how, so at this point, anyone learning in this lesson should be fluent with these basic operations, taking absolute value. So now from that previous understanding, now we define our absolute value function. It means for any inputs, it could be negative, it could be positive, and it could even be 0. But we take an input, but then the rule of the function says we take the absolute value on the input. So that's why absolute value of -1 equals 1. Okay, and so now how about f of 2? So for f of 2, okay, it gives me absolute value of 2 because the rule said so. And absolute value of a number that's already positive is just simply the number itself. Okay, so f of 2 has outputs 2. F of 0 equals, the rule says take absolute value of 0. And so absolute value of 0 equals 0. Okay, and then again, f of -5 equals absolute value of -5, which equals +5 again. All right, and so now in that way, here's the graph. All right, with our empty graphing space right here, this is the graph for the absolute value function. Okay, it's the graph for absolute value function. All right, so why is it like that? Why does the graph look like that? Of course, I will have supplementary video clips explaining in more detail steps of how it came like this. But think about right here in these the table in these values that we can put these values in the table of values, and that will explain the reason why. So you can think of a table of value as following. I've had -1, I've had 0, I've had 2, and I've had -5. Okay, and the function output was 1, 0, 2, and 5. Okay, and this is why now let me bring up that graph right there. Okay, according to the table of values. Okay, so when x equals -1, when x equals -1, okay, then our output is this height right here being 1. And now allow me to zoom it in a little bit. Okay, and then when x equals 0, our input being 0, then our output here is 0. That's why we have that vertex right there, that little corner that hits right on the x-axis at x equals 0. When our input equals 2, we have the output being 2. And that's why it's rising back. So the line here was going down from the left to the right and then hits to a 0 and swing back. It forms a nice right angle right here. When x equals -5, the output was +5. That's why for any negative inputs, we have a positive output. That's why it's like that. They're all on the positive, vertical positive side above the x-axis. Okay, and that's how it explains for the nature of this absolute value function. So as a main characteristic, I usually advise my students when classes are face-to-face. When I'm teaching in a face-to-face course, I advise my students to imagine the absolute value function here as a V shape. It is a V shape. It's a famous V shape, 90 degree at the V, 90 degree at the angle for V right there. And with this very basic one, with this toolkit, f of x equals absolute value, the corner of the V, the vertex of the V is right at the origin, right here. All right, and so that's how, that's the graph of this absolute value function. And so now I can just simply put away the graph, the nice looking graph, but see, put in your imagination when anytime the name absolute value function is rang to your ear, is brought to your ear, it is brought to your attention, have in your imagination the following graph. Doesn't have to be anything fancy, but it's a V shape. 45 degrees here, another 45 degrees here in the two corners. That's why it's make that V shape right there. I'm not an artist, so forgive me if my 45 degrees lines are not too perfect, but that's the idea. So right there is see this one right here, that's the graph for f of x equals absolute value of x. That's how easy it is to get the graph for that function, and it's how easy it is to keep that shape, that V shape in mind, and the vertex of that V is right at the origin 0, 0. Okay, that's enough of the characteristic of your absolute value function as one among the toolkit functions right there. All right. All right, so now let's look at our next one here. So here's the name is given a little loosely among the textbooks out there. So not all authors and not all professors agree with the same name, but they all bring up this a similar meaning. So now the function I'm about to introduce here is the f of x defined to be x squared. So we have a specific rule here again. For every input, we're gonna square the outputs. So squaring is a very elementary operation. We raise up to the square power. Okay, so for any inputs, the rule says we square the inputs. That's one among the toolkit functions that I'm about to introduce here. Another toolkit function. Okay, so this toolkit function, many textbook authors call this the quadratic function. Okay, I agree, no objection. But I would like allow me to call this function a little more specific. How about let's call it it's a simple quadratic, because quadratic itself is a family, and there are many other quadratic functions. So I don't want to just overuse this term quadratic function, because there's an entire sky about quadratic functions out there. This is only one among the quadratic functions. So with this specific one, allow me to regard to this as the simple quadratic function. But in the end, this function itself, f of x equals x squared, is one among the ToolKit functions. Okay, and so as the rule is stated here, according to the rule that you are seeing right here, and more experience for you to learn, to get comfortable with evaluating. But see, when you pick a negative input, f of negative 2, functional notation is indicating that this is the input. So we let x equals negative 2. We substitute that into the function. I highly recommend using parentheses anytime we're substituting values in. So minus 2, but the rule says we square that, and that's why I put parentheses around. Now, in my teaching experience, be careful with this, and that's why I was saying out loud earlier, I love to put negative, and I highly recommend to put negative inputs, or put all inputs in parentheses, okay? Because when it comes to case like this, now what happened if you skip the parentheses and you wrote like this? This is incorrect right here, in the sense that according to the order of operations, then the square here is only for that 2. Okay, the square here is only effective to that 2, so it gives you the answer being negative 4, which is incorrect. The real truth here, we want to square the inputs. The input is negative 2 itself, so we must square the entire negative. That's why putting things in parentheses keep things very organized and clear right there. Okay, so the output here is supposedly or tentatively positive 4. This is the correct one. This is the incorrect one, because skipping the parentheses will make you think that the square here is only on that 2, and then the negative sign here comes after. Remember PEMDAS, okay? If without parentheses, then exponent comes before multiplication and division, and even further before adding and subtracting. That's why when you're seeing a notation like this, people internationally will understand that the answer is a negative 4, which is not what's intended for this case. Okay, so be careful with your PEMDAS, with your order of operations. Okay, so now we're looking at 2. Okay, so now this is 2 in parentheses. I'm substituting 2 into this rule, and then I'm squaring that, and now legally it's 4 again. All right, and then 0, I can have a 0 in parentheses squared. The answer is 0. That's just to get comfortable with the function. So that's just to briefly introduce the meaning, okay, of this function and what it does according to its rule over here. But now let's look at the graph right there. Okay. So in my empty graphing space, all right, so here we go. The simple quadratic function has the graph as following, right there. Okay, so let's see. At least let's see and find out how it's consistent with what I've shown on the board earlier. When x equals negative 2, on the x-axis, when it comes to negative 2, we came out to the outputs being positive 4. Okay, and this is why. When x is negative 2, the output is positive 4. So we are right at that point on this graph. Okay, on this graph. And then now again, when x equals positive 2, we came to the output 4. So on the x-axis, when it's x equals 2, we have output equals 4. Another vertical value being 4 here. So that's why now when x equals 2, we have output equals 4. That's why we have another point here, right here on that nice parabola. And I believe you have seen another function throughout our earlier examples where the graph was extremely familiar, extremely similar to this one right here. And yes, this is a parabola, and see, the name here of our function is a quadratic function. Okay, so anytime you have a quadratic function, your graph will be a parabola. And then we will spend some time later on throughout our time learning pre-calculus together to study about the quadratic functions, the advanced properties, the more detailed properties of the quadratic functions. Okay, and then just as I was sketching down here on the board here, when input equals 0, we have an output equals 0. It's just the way how that operation is. Okay, we have an output, squaring of that input 0 give me an output being 0, and this is the reason why we have a 0 right here on the x-axis. When x equals 0, our graph sink down vertically down to 0 as well. So right at that point, we have a 0, 0. Okay, and that's our graph. So now from this point on, and with the graph we've just seen right here, okay, and I'm still leaving that on at the corner of our screen right there, then it's a parabola, a nice cup. And you have seen this cup in some of the other examples before. In some other example problems, there was also a cup looking just like this, maybe being positioned differently, just slightly different position, but it's in the end it's a cup. Okay, and so just like that, for this specific f of x equals x squared, you can close your eyes and imagine the following. So anytime the term simple quadratic function comes to your mind right here, come to your attention, then imagine for yourself a cup. Okay, imagine for yourself a cup. And I intended to draw exactly with the vertex at the origin, but I'm already off scale right there because I'm a human being. You know, I can't reach that nice accuracy like the computer can do. Okay, but see, the vertex is right at the origin, and it's a cup. That's fair enough. Okay, and then we find my supplementary videos so that I can show precisely what these points are that made up that points. But in the end, what should have caught your attention is a nice parabola. Okay, pointing up, it's a cup that's holding water. It's not this cup. Some other parabolas will give a cup like this. Okay, but that's not for this function. So it's still a cup, but a cup like this is called, to me, I would say it's spilling water away. Whereas the cup we are looking at for this function is a cup that's holding water. Have that characteristic in mind, in your mind. Okay, and then the bottom of that cup, the vertex, formally speaking, the vertex of that cup is right at the origin. And another property, this cup specifically is symmetric right through the y-axis. Okay, think about the y-axis is acting as the mirror image of one side of your cup, and then the other side is just the image of that through the y-axis. Okay, and so, and then all of that symmetry, and we will also have a time throughout our course here learning together to talk about the symmetry on any graph like this. So for now, I just briefly introduced, but that's the shape of your basic of your simple quadratic function. Okay. All right, and now let's look at the next one, being the function defined with the following rule: f of x equals x cubed. Okay, so the rule of this function says for every input we raise the inputs to the third power. That's why it's called x cubed. I was stating it earlier. Okay, so yes, as the operation itself is called, right? So this function is called, and again, many textbook authors out there refer to this as cubic function. But as a matter of fact, cubic function is more, to me, is more like an entire family of cubics. As long as you reach to a high power, and we will study all of that later on throughout the course here together. But this is only one term, coefficient 1, and one single variable being raised to a third power. Allow me in this lesson to call this, it's a simple cubic. It's a simple cubic. Now, I won't get too far into the details, okay, because I want, some people have seen this, some people haven't in your prerequisite course. So if you have seen this before, then I can move on at a fast pace here. And then, if you feel like what my introduction here on this particular function is a little too fast for your pace, find my supplementary video lesson so that I can just simply pinpoint how the graph was constructed from every elementary steps, including the table values. Okay, but in this case right here, but for this particular graph, now with my empty graphing space, this is the graph for the cubic function. Okay, this is the graph for the cubic function. All right, so as a characteristic, it looks like a waterfall, but think about it falling from the right to the left. Okay, the waterfall is going that way, right there. Okay, falling from the right to the left. That's a waterfall right there. Or it's rising from the left to the right. It's rising. I mean, it's a little awkward that I've been highly recommending students of mine to view the graph always a lot of times from the left to the right, but for a shape like this, to make it easy in some rare instances, like for this case right here, to make it easy for you to remember, then it's a waterfall, but it falls from the right to the left. It falls like in that nice bent curve like that. Okay, and then let's check for some consistency right here. Okay, so the rule says we raise every input to the cube. So I noticed when x equals 0 on the graph again, and it happens right there on the graph that you're seeing. So when x equals 0, the rule stated that we raise that input to the third power. And that's why we have that output being 0. And so this is what results in, graphically speaking, we have that point right at 0, 0 right here. Okay, and then again, I'm going to try what happened when x equals 1. Okay, when input equals specifically 1. The rule stated that we need to raise the input to the third power, and so it gives me an output being 1, because 1 cubed equals 1. It's just simple algebraic rule right there. But now, once again on the graph, let's see if it's consistent with our calculation. See, when x equals 1 on the horizontal axis right here, we came to that height, that vertical height being 1. Okay, and then same way right here, when x equals -1, the graph here reads -1 for the output. Let's see if the calculation agrees with that. Okay, f of -1 equals, now the rule says -1 raised to the third power, -1 times -1 times -1. The final answer is -1. And that's why we had a point -1, -1. Agree consistently with this graph right here, where we have that point being right there on the graph. Okay, and so now that's what it looks like for the graph of a cubic function. Okay, and I can put it out further out in a further the zoom right there. And so now, again, from this point on, anytime the term or the name simple cubic function is brought to your attention, then you see in my imagination, this is what I highly recommend to keep in mind right here. Think of a waterfall, okay? But it falls, think of the waterfall through the origin and falling from the right to the left. And when we're just giving a sketch, see, there's a difference between doing it with human being capability and doing it versus machine. So we don't have to do that with that kind of precision that machine can give, but we're just giving something that's descriptive enough. And so waterfall, it's falling down and going a little flat here, and it's continuing to fall. That's fair enough to be a simple cubic. And see, it has this point here at 0, 0. It has a 1 up to 1, okay, and it has a -1 to a -1 down here. Those 3 points are good enough to define this waterfall for the simple cubic function. All right. And now among the ToolKit functions, allow me to introduce another one. So here we're looking at, how about another function here? F of x is defined where the rule is saying that we're going to take the square root of x. We're going to take the square root on every input given to the function. All right. And so this function, yes, the name is saying it's called the square root function. It's a square root function. And allow me to additionally call this a simple square root, because to me, in my teaching experience, in my experience doing math, square root is not only just this one function. There's an entire large family of square root functions out there. And so on this specific one, allow me to call that a simple square root function like that. Okay, but so now this square root function. Now let me quickly throw in the graph here first, and then we will understand what's going on with that. All right, so here we go. That's our empty graphing space right here. And let me now pop out that the graph for the square root function. So there we go. That's the graph for the square root function. And I'm going to drag and click, hold, and drag my graphing space with desmos.com so that I can move it out further, so that viewers can see more view, having more better view of that. Okay. Yes, in the way how it looks, and your eyes are seeing it. Okay. Then the graph from the left to the right, the graph extends infinitely to the right hand side, and it's going in a bent curve like this. Okay, but the graph actually stops right at 0 over here, or the graph doesn't have any parts on the negative side right here. As a matter of fact, see, the graph starts at x equals 0. If we're thinking from the left to the right, the graph starts from x equals 0 and running to the right hand side and has no stop. But if we're looking from the right to the left, then the graph kind of stops right here. That's why I kind of use that term. Okay, but in the end, you see, there's a limit right here. There's ending point right there, a clear, specific ending point right there, and then the graph keeps extending infinitely out to the right-hand side. Okay, so as a characteristic of the graph, anytime simple square root function, anytime that name is brought to your attention, then this is what I'm seeing. This is what I recommend to keep in your imagination. Starts as 0, okay? Making a bent curve going that way. As another truth right here, this is a sideways parabola where you don't draw the other part, okay, of the parabola. So we only take half of that sideways parabola, the positive piece only, okay? And so when it comes to these, you are more than welcome to find, the interpretations from many professors. My way of interpreting it is, it's containing some details, and other professors can also have their own way to. We certainly have a few common ways, a few similarities, a few common things that we have to cover. Okay, but then there are also some other details that different professors cover on different things right here. So when it comes to these ToolKit functions, find as many video lessons as possible when it talks about these, and the more you find, the more it emphasizes the more you find, the more you enhance your understanding. Okay, so I see this as a sideways parabola, but we only take the positive half of that. Okay, and it starts only at x equals 0, and then it keeps extending out further out to the right hand side. Now let's look even further, a little bit more. Why is it only ending right here? Okay, or thinking from the left to the right, why does it have to strictly start at x equals 0? Nothing else, no other x values, or no other part of the graph present here to the left hand side. Okay, because here's the thing. Well, in our experience with real numbers, okay, we can take f of 4. When input is 4, it's a positive value. The operation says we take square root of positive 4, and we have a successful value being 2. No one can argue about that. We can take the inputs being 1. So f of 1 reads, input equals 1. The rule says we take square root of 1. We have an output being 1. Okay? And this is the reason why we have a couple of those values right here. When x equals 4 on the graph, we have y equals 2 right here. Okay, just like how it happens, just like what it happens right there. Okay, and then when input is 1, then we saw on the graph right there that the output is 1 according to the operation. And so further, when input comes to 0, just like that, when this is f of 0 right there. Okay, so input is 0. So we have f of 0, so the output comes out being square root of 0, which is a 0. Okay, and that's why we have that point. But now I was on my way, and now I am getting to that point right there. Why do we have the graph only start here? Okay, why do we have the graph only start there? Nothing else beyond this x equals 0 to the left. Okay, because, well, you're welcome to try. Okay, throw in -2. And as I have mentioned already in some of the earlier lessons right here, when we're studying this course, we're only staying in the real numbers. So within the real numbers, we cannot take square root of a negative value. Well, the rule says we take the square root of the input. Okay, but this function, in the way how this function is defined, we cannot. If we're substituting in a negative input, we are ending up with square root of a negative value, which is undefined. Okay, this is undefined. We are not able to take square root of a negative value unless we have some experience with the imaginary number or complex numbers. But none of that is being covered here. Okay, and that is the reason why this graph does not have any representation on the negative side, right there, on the part where x is negative. Okay, and then later on when I will talk about domain and range of a function, it will better explain about that. Okay, and so now in the end, that's the famous shape of your simple square root function. Okay, and once again, if you're looking for other details and as well as how do we build, how do we graph this thing, you know, from the very elementary step right there, find my supplementary video lesson so that I can show from every single little step how we ended up with this graph. Okay. And now another one, and hopefully with these the last ones right here, I can start picking up pace a little bit right here. So another one here among the ToolKit function is defined to be the cube root of x. Okay, and so with this one here, many textbook authors refer to this as a cube root. Okay, cube root function. But I would call this simple cube root function. It's just my added term for that to make it a little more clear, because cube root itself, there are many cube root functions. But this specific one right here is a simple cube root function. All right, and so just like that, the rule says for every input we take the cube root of the inputs. Okay, so now let me quickly show the graph of the cube root function. All right, so here we go back to our empty graphing space right here. And now this is the graph for cube root function. Okay, and so when x equals 1, we have the output equals 1 because we're looking at f of 1 equals cube root of 1, which is understandable enough, which is 1. Okay, and that's why we result in this point right here on the graph. X equals 1, y equals 1. Okay, and then there's this point right here being 0, 0. Okay, this is input equals 0 and output equals 0. This is because when the function takes input 0, that means the rules of the function says we take the cube root of 0. And cube root of 0, there's nothing problematic about cube root of 0. The answer is 0. Okay, and that's the reason why we have this point right here. And then cube root of -1. Okay, cube root of -1 is -1, or we have that point right there, -1 comma -1 right on the graph. Okay, and so that is because cube root of, the function with inputs -1 gives me cube root of -1, and that is -1. Now, square root that we have covered earlier algebraically does not take negative inputs, but cube roots, or generally any odd root, okay, will take negative inputs and give us that negative answer. Okay, so cube root of -1 equals negative, and this is the reason why we have on the graph right here, it shows there's a point at -1 comma -1. So anyone is learning along here and taking the notes right here, you can go ahead and note these special points with your with this graph, the cube root function right here. Okay, and so with this function, anytime it comes to your attention, anytime the name is simple cube root, okay, then it looks almost, it's the way how I recommend my students to imagine, think about the square root. It's almost like the square root as far as making a sketch. So the shape is almost like a square root, but we have another piece on the other side. That's cube root. Okay, so almost, I'm not saying it is the square root function, almost like the square root on this positive side, and then it has that duplicates on the opposite side right here. It does have some symmetry, and we will cover in more detail about the symmetry here when we get to learning about the transformation and all that. Okay, and symmetry of on specifically any graph. All right. And now I am going to introduce another ToolKit function. F of x equals 1 over x with the rule 1 divided by the input. Okay, so f of x equals 1 over x here. So this is, with this function, I agree with many of the authors out there's name for this function. It's called a reciprocal function. Okay. Reciprocal function. So that's the name for that, this reciprocal function. And so with this reciprocal function, before I rush into throwing in the graph, I just want anyone to understand this. We're a human on earth. We just can't divide by the 0. So this function, f of 0, means, as the way how the rule is stated here, 1 divided by the input. So when you're giving it an input 0, f of 0 means 1 over 0. But we are, as I said earlier, we are human on earth. We have tried for many centuries, still unsuccessful. So it's an undefined value. We don't know how to divide by 0. Okay, it's still an undefined value. So this function will take any other inputs except 0. Okay, it takes any other inputs except 0. And later on, when I discuss, when it comes to, we give that discussion about domain and range of the function, it will become more clear. But so now, as far as the input, it's just see the way how the operation is defined. So simple to similar to square root function I introduced earlier. Square root function just cannot take negative inputs. Okay, 0 is fine for square root, and then it could not take negative input. So like that, similar to that. Now for reciprocal function, it takes any inputs. F of -1 means, or generally a negative value. We can go 1 divided by -1, we have a -1. We can take a positive value, okay, like a 2. Okay, it's 1 over 2, and it's completely fine. 1 over 2 is a 0.5 numerically, or just 1/2 as a fraction, but we just can't divide by 0. So this input here is undefined. The function value, the function output value is undefined. Okay, so taking account of all of that known fact right there, now it's time for me to show the graph. Okay, and again, just how we sketch that graph, how we construct this graph from scratch with all table, with an entire table of values. Allow me to save that in a separate video, because that's only for optional viewing in case somebody have never seen any of these toolkits function before. But usually it's assumed that by the time you arrive at this video lesson, which is intended for a pre-calculus course, and you should have seen all of these toolkits functions anywhere here and there. Here, which is more like reviewing over those functions. Okay, and so now here's my empty graphing space, and allow me to zoom it out a little further out, okay, in pretty far scale, so that you can see a good have a good view of the graph. Okay, so now here's the graph for 1 over x. All right, so I pointed out that when x equals 1, we have a point 1, which is right here. Okay, and see 1 comma 1. When x equals 1, we have a point right there. And then let me put it in even closer zoom right there. Okay, a completely full screen right here. Then when x equals 1, we have 1 comma 1. When x equals -1, we have output vertical height being -1. Okay, so -1 comma -1. So, but now we just see there's that phenomena that when x equals 0, really do we have a point that hits the graph? Nope, I can keep dragging it out, and we don't see it. When x equals 0, the graph will not have a point that represents the height at x equals 0. Okay, and just like that, when x equals 0, on this left side, negative side, we won't see a part where the graph crosses through, x equals 0. So this behavior is, in other words, asymptotic. We will get to that later. This vertical line right here is called a vertical asymptote. X equals 0, the y-axis is called a vertical asymptote. And this horizontal x-axis right here is called a horizontal asymptote. So the 1 over x function, this reciprocal function here has two asymptotes. There's a vertical asymptote, as you're seeing on the graph, and there's a horizontal asymptote, as you're seeing there. Okay? And then later on, we will come back and investigate this even further. And once again, if anyone desire to see the step-by-step construction of that graph, then find my supplementary video so that I can show from table of values to how we finish successfully with that. But in the end, as a major characteristic to remember, see, the graph is broken down into two separate pieces, as you are currently seeing on the graph, like that, on the picture showing. So the one piece is like this. It gets closer, it keeps getting closer to the y-axis, and then it rises higher. In the same way here, it keeps getting closer to the horizontal axis and gets further out. Okay, then so that same similar piece being opposites, being symmetric down here. So in either way, on either side of the y-axis, from the right-hand side, from the left-hand side, the graph is attempting to get closer, to get close to to get close to x equals 0, to get close to the y-axis, but it will never cross through. See, the y-axis is here, and you will never find a part of the graph that crosses through on this function. You will never find any piece of the graph that crosses through the y-axis. The same with the x-axis here. You won't find any piece of the graph that crosses through the x-axis at all. Okay, so that's the major characteristic of this reciprocal function. All right. And the last one among the toolkit functions that I would like to introduce is the function with the rule f of x equals 1 over x squared function. Okay, 1 over x squared function. And then the name here, many authors refer to this as reciprocal squared. Okay, this is a reciprocal squared function. All right, so it has that reciprocal part. See, it's similar to the 1 over x. Okay, but the input here is being squared in the denominator, That's why it's squared here. Okay, so reciprocal squared. All right, so now, just like that, it has a denominator. This rule here has an expression in the denominator. So think about this. Okay, when we substitute in x equals 0, it gives us, according to the way how the rule is and according to how function works in general, and we're looking at 1 divided by the square of the input, 1 divided by the square of the input. But the square of the input here in this case, which input specifically 0, we're looking at a 1 over 0, which is another undefined. Because we are back to that same crisis earlier, that as long as we're a human on earth, we just can't divide by 0. Okay, we can't divide any value by a 0. So this input is unacceptable. Okay, or given an undefined output value for our current function here, the reciprocal square. Okay, but other than that, so this reciprocal square is a little more special than the ordinary reciprocal, in a sense that, see, now we're looking at negative inputs, for example. Okay, then that means it's a 1 divided by -1 all squared. See, again, you have seen enough of my video lessons up to this point, but anytime I'm substituting values in, I use parentheses, because now that's making a big impact here. 1 divided by, but -1 all square means it's a positive 1 in the denominator. Okay, so 1 divided by 1 gives me positive 1. Okay, and then, so that's the output and that's the input. But now when you're also at positive 1 for the inputs, when f of 1, we're taking x equals 1 for the inputs, we get, according to the rule, it's 1 over 1 squared, and that gives me a 1 over 1, because 1 squared equals 1. Okay, and then that equals 1. Okay, so now negative input and positive inputs all gives me the same, all give me positive output. Okay, because it's the way it is, our reciprocal is being squared. Okay, our reciprocal being squared. And so in that way, now let's look at the graph. In that way, now you're ready to look at the graph. And again, if anyone is looking for more the detailed construction of the graph, then find my supplementary video lesson where I can should be able to show all of the elementary steps, okay, of how we construct this graph, and more detailed structure there. All right, so now back to our graphing space here. The graph of 1 over x squared is having a shape like this. All right, so just like that, just like what I pointed out earlier, we just cannot take x equals 0, and that's what explains for this graph is giving a permanent gap. See, there will be no part of the graph crossing through the y-axis, because right where the y-axis is, it's x equals 0. The graph, we will not have any part of the graph. See, I keep dragging it down, it's hopeless. We won't find a part of the graph that crosses through the y-axis. Okay, and so that's the whole idea about this function. And so, and then on the two other side right here, see, the machine is also having some difficulty showing the difference, but the idea now is the graph is getting closer and closer to each of these horizontal axes, but will never hit the axis as well. So that's why this function again has a vertical asymptote being the y-axis, and also having a horizontal asymptote being the x-axis. Okay, and that's the picture of this 1 over x squared graph like that. All right.